So once again, just focusing on one part of the process in which we're creating flexible, transparent electronics. In our case, using flexographic printing, but that's not necessarily the focus here. It could be for lots of different modalities. I think we all know that the drive behind doing some of these sorts of products, particularly in terms of antenna, with 5G coming along, needing more antenna in more spaces to eliminate dead zones, given the higher frequency, as well as not having those be so apparent to everyone in their particular environments. Having it be a little bit more pleasing. So we're working with a number of companies that are focused on creating these transparent or even flexible antenna in the automotive space, but also industrial for indoor use in offices and public spaces, etc. Again, here's just a very high level description of the process that we're going through to create these designs to make them printable. And again, it could be in a variety of situations. So in the case of antenna, I mean, this again could apply to other types of products, heaters, etc. But generally, you're going to be working with a specialized simulation software package. In this case, could be ANSYS, it could be EMWorks. There's a variety of ones that allow someone who's an RF specialist to design something and then simulate the performance of an antenna before they actually put it to a product. Generally, once there's fairly satisfied with the design, it would probably go to an FR4 board type of prototype to test the performance in that mode. It's a very inexpensive way to get started. Before you actually commit to the another process that may be more cumbersome. From there, once you're satisfied with that design, you're going to export that to a CAD file or a DXF file, or it even could be like an Adobe Illustrator or some other vector-based file. From there, you're going to take it and essentially replace all your solid copper or conductive areas, with a mesh. And the width, the line width, and the pitch of that mesh is going to be determined based on the target level of sheet resistance you're looking for. And there's also a transparency trade-off. So the more dense you make it, obviously, the less transparent it becomes. And you need certain areas where they have to be, much more dense. For example, your contact pads, et cetera, where other areas is going to be much more sparse. And again, this is all dependent on the ink you're using, the print modality, whether that's a flexo or not. All will determine what's the right mix of line width and pitch to fill these various areas. And then from there, you're going to have to render that vector file into a bitmap, essentially, that your imaging system can ingest. Right. In this case, it may be something where you're creating a printing plate. And here's an actual concept that we've worked with the wireless company to develop. You can see here up in the top left is what the artwork or the vector diagram looks like. On the bottom is actually the prototype itself with the connector. It's not a finished product, so it's not designed to be completely invisible at this point. But you can imagine that this would be something that would be up in a ceiling, and the wires and connector behind it wouldn't be exposed, and just the transparent, in this case, acrylic thing would be there and essentially unnoticeable. But you can see the performance here is excellent. It's everywhere from 600 megahertz all the way up over 6 gigahertz. So it's appropriate for everything from Wi-Fi to LTE to 5G. And just another thought when we're talking about additive manufacturing is we also have the ability to do a covert layer. So you can have your functional layer with your conductive materials, but then make a reverse of that pattern, if you will, for non-conductive material and essentially, make the design disappear. So I will leave it with that, and hope to see
Excellent.
everybody in the sessions.